Hello, welcome to the next adventure in the world of electricity and magnetism. For the next two classes or three classes, we're going to focus on electricity, and then we'll move on to magnetism. But first off, let's do a bit of review from back in grade 9 because it's been a while since we've talked about electricity. All right, so back in grade 9, you would have learned these concepts over here. The text in blue you don't need to copy. Again, copies of my PowerPoint are all available in Google Classroom, and you're watching the video right now. So if you do need to rewind in time, you can go off and rewind back and look at it. All right. So what do we know so far from back in grade 9? Electricity is a continuous flow of electrons in a circuit. All right. And in the circuit, they require something to push the electrons. That's the whole purpose of a cell or a bunch of cells together called a battery. All right. In electronics, we often call it EMF. Not for electromagnetic pulse or radiation, but electromotive force. That's what it means. Okay. If you're curious, EMF stands for electromotive force. And that's just the source that forces electrons to move. Because if there's nothing to push the electrons to move, they'll just stay stationary in the circuit and no electricity will flow. All right. First off, let's just compare between the picture representation and the schematic representation of these components. We'll start off with our EMF, our source. Okay, it's either a cell, a battery of cells, or an electrical outlet. All right, and as a schematic representation, I think this is good enough for us for now. Okay, that represents one cell. We also need to have a load in the circuit. With a light bulb, I think this is the standard way to draw it. We just give it a little swirl, put a circle around it, and call it a light bulb. That's good enough. If we need to describe a resistor, then it's just a bunch of zigzags, and I think that's what we'll be using most in this unit. All right, we won't be referring anything with light bulbs, but we'll be referring them with loads represented by a resistor. Okay, and lastly, to make all the magic happen, you need to have a circuit path. And to control the flow of the circuit path will include a switch. Right now, with the switch open, you'll notice there's no full path for the electrons to flow, and that's why the light bulb remains off. But the moment that you close the circuit, now the electrons are able to flow. One common misconception people have is that electrons, when they flow through, they travel at the speed of light. Okay, and unfortunately, that's not possible. If electrons traveled at the speed of light, for one thing, their momentum will probably cause them to fly off the edge of the circuit. Okay, they'll just fly right off because they're traveling at 3 times 10 to the 8 meters per second. All right. Another thing is that you'll need to also factor in energy required to accelerate that mass of an electron so that it can flow through the circuit. So that's the problem about describing electricity as electrons traveling at the speed of light. But then you'll say, hey, why is it that when I turn on a switch, the light turns on immediately? All right. And the answer to that is that the electrons don't travel at the speed of light. It's the energy that travels at the speed of light. Okay. You can think about it kind of like Newton's cradle. I'll just draw a quick little sketch of a space over here. Okay. Good old Newton's cradle, you know, the thing where there's a string, there's a mass, and there's a bunch of other masses all hanging, often seen at doctor's offices for whatever reason. All right. And the moment that you let go of the first mass, the energy almost instantaneously passes through to the mass on the far right. Right. If you ever play with it in the future, you'll see that. It's like, boom, the energy just immediately gets to the other side. That's what's really happening in an electric circuit. All right. The electrons don't travel at the speed of light. It's the energy that they carry that knocks against the next electron, which then propagates through the circuit. And that definitely travels at 3 times 10 to the 8 meters per second. Okay. So the energy does flow at 3 times 10 to the 8 meters per second. Okay. So then there's the other question, which is, well, then how fast are electrons really flowing? Again, in this demonstration over here in the animation, it actually is too fast. All right. In real life, electrons, they really crawl. Okay. They only crawl at a few centimeters per second. Okay. It is often said that, you know, when you try to start the engine of your car demands around 100 amperes just to turn over the engine. All right. So you have to crank your car for at least 10 minutes before the electron from the battery travels all the way through the circuit, through your starter motor, and all the way back. And in 10 minutes of cranking, your batteries would be dead. So the electrons in their lifetime before you charge the battery again, they won't make it back. Okay. So the energy travels at the speed of light, not the electrons. Again, just small little technical definitions. I'm not going to be too fussy about it over here, but by definition, when you have just a single AA, You just have a cell. All right, and a cell by definition is an individual entity with its own anode, its own electrodes, and its own fluids inside. Its own to create that individual storage cell. Hence its name, right? But if you have a bunch of cells all connected together in series, they actually borrow from a military term. When you have a bunch of soldiers all lined up together, it's often known as a battery of soldiers. So you have a battery of cells, and today, out of sheer laziness, we just call it a battery. Okay, and the schematic symbols are slightly different. Again, I'm not going to be that fussy about it when you note it out in your notes in the future. All right, so I just want to tell you that technically speaking, the one on the left represents a cell, and when you have a battery of cells, then you have a battery. Okay, so most of the time we're using the terms incorrectly in society. There's only one case we are using it correct, and it's when you end up using a 9-volt battery. I don't know if you guys ever tried dissecting one before, but if you ever take one apart, a 9-volt battery is made up of 6 tiny little cells inside. It's not a magic trick, for real. You snap it apart, you'll see 6 cells in there. Okay, another thing that you learned back in grade 9, and I have no problems at all using this as an analogy because it does more or less work, all right? Where you try to describe electricity through the process of Niagara Falls, where you would describe the fact that the voltage in a water droplet can be dictated by its height. So the higher the droplet is on Niagara Falls, the higher the voltage, all right? So low voltages are close to the ground, and high voltages or high potential differences are far away from the ground, okay? Current, on the other hand, is how many of these water droplets are falling at once. In other words, how wide is Niagara Falls? Okay, so the height describes the voltage, and the width describes the current. All right, and again, this analogy does make sense. All right, if you replace water droplets, which, as they fall on you, they're rather harmless, but let's say you replace the water droplets with pennies. Okay, you drop a penny a meter above a person's head. Ouch. You take that penny and you bring it, all the way up to the top of CN Tower, and you drop it on the top of a person's head. They'll probably still say, ouch. Will that one penny kill them? It'll hurt a lot. All right. So that one penny will not be the factor that a person will be seriously injured. Instead, if you drop a whole bucket load of pennies from the top of the CN Tower, that's where the danger comes in. And that's what we talk about with regards to voltage and current. Voltage doesn't necessarily kill you. It's the current that can cause your heart to stop beating. Another thing is that, again, this is a 3-dimensional picture or a 2-dimensional picture, all right, where voltage is in this dimension and current is in this dimension. So if you fill it up all together, you have a surface area. And anytime that you have a surface area, you can multiply the width and the height. And by definition, that's what power is. So that's one of the first formulas you learned back in grade 9. Power is equal to current times voltage. Okay? That's one of the formulas that you've learned. As I mentioned, a voltage, yeah, it can hurt, but it doesn't necessarily kill you. All right. There's pranks that you might have done on your friends, growing up, where you'd walk on the carpet on a nice dry day. All right. And as you rub against the carpet, you sneak up to your friend and you touch them on the ear or you touch them on the nose, and your friend goes, ow, because you just transferred a potential difference of, 10,000 volts or more. All right. So that voltage is very high, but other than annoying your friend, it didn't really kill them. There wasn't enough current flowing through at that moment to actually cause any significant damage. All right, you need to have a large quantity of current flowing for it to be dangerous. Okay, so it's the current that's dangerous, not necessarily the voltage. Sure, they go hand in hand because as the voltage increases, your chances of becoming injured will increase as well. All right, and that has to do with the fact that our bodies have an internal resistance. So I think those are about the only 2 formulas that you need to carry on from. Well, there's 2 of 4. All right, 2 of the formulas is P is equal to IV. That's from back in grade 9. Don't worry, we'll have notes on this afterwards. And V is equal to IR. That's the next formula that we'll cover. I don't know about today, but I think we'll cover it by tomorrow. Okay, so those are two of the 4 equations that we learned back in grade 9. I'm just quickly reviewing through it. Normally, I would have you guys all play with this activity together with me, and it's a lot of fun. Unfortunately, we're not together right now. So I'll just tell you what the activity is, and hopefully you can visually appreciate what's going on here. And then I'll reuse this analogy slightly differently afterwards. All right, just to make sure that you have a good foundation understanding of what's going on in a circuit. So what I would have is I would have all the students line up around in a circle. Then I'd have these little name tags or these little dog tags for the students. One kid is lucky enough to have this dog tag, and the other one is lucky enough to have that one. And the third one, I'll just give it to them just so that they have something to do, and that's it. All right, and they'd all be standing around in a circle. Now, for the person who has the one of the battery or the cell, they're forced to have the bucket that they need to carry around. And the bucket is always filled up with these tiny little balls. They could be ping pong balls, they could be little eggshells, or they could even be golf balls. It doesn't matter. It's just something for the kids to pick up and pass around. And then this is what I would have the students do. All right, the person who has that basket full of little balls around, they're the ones who are the electromotive force. They're the ones who give the electrons energy to move. So what they're going to do is they're going to lift it up high into the sky just to tell the rest of the class that, hey, this electron has a lot of energy now, right? It has a big potential amount of energy. Okay, so that's what's going to happen. That student is going to bring that electron, and I'll just use an arrow up just to indicate that the electron is really high. Then everybody else in the classroom, as they're standing around, all daisy chained together, they'll just carry that electron all the way across the circuit. Now, for one thing, if the switch is left open, there's no path for that electron to go back to the source, so not much really happens with the switch open. You need the switch closed in order for the electrons to keep on traveling through. Now, here's the thing to point out, all right? The electrons will have lots and lots of energy through the circuit until they hit their first load. And seeing that this is the only load in the circuit, the load will take that energy and drop all that energy. And usually that second student who has the load picture on them, what they need to do is they need to take it, they need to spin around and go, woo, as they lose the energy, and then the energy gets down to the bottom, and then they need to carry that energy through the rest of the class. So the rest of the students act as the electrical circuit, and I'm putting an arrow down just to tell you that you'd be holding that electron nice and low until you return it back to the source, where the source will take that dead electron and bring it back to life again, so it has energy to go around one more time. All right, and that's the essence of how circuits behave. The EMF gives the electrons energy, the electrons move through the circuit, energy gets consumed by the load, kind of like if you play Pac-Man and the ghosts get gobbled up. Now they're just tiny little eyes, and they run all the way back to the source to be rejuvenated one more time. Okay, then I had the students go off and build this version of the circuit. And I hope you can guess what's going to happen here. All right, you'll notice that the source, or the EMF, this person has to now work twice as hard, because now this person needs to carry twice as many balls across, where one of them will be allocated to one light bulb and another one will be allocated to the second light bulb. All right, and then it'll be split up. Eventually, this person over here, they got to work hard as well, because they need to gather all of them, and you're back to twice as many as they return back to the EMF. Okay, again, it's a whole lot more fun if we do it in person. Maybe if you have a large family at home or cousins, you can try doing this yourself just to see what happens here. All right, so you can see that the current flow is a lot bigger right over here, then it gets split off. Does it necessarily have to be split off 50-50? No, not really, because if one light bulb is, let's say, bigger and more demanding, it's gonna demand more electrons to flow through it, or it's gonna demand more current. Okay, but nevertheless, in this analogy over here, you can see that electrons, they don't disappear. Yes, more of them are used, but they don't disappear from the circuit. They're constantly recycled, and the EMF just gives the electrons extra energy to work through. And then in case 3, what I have is that I have the two people, the light bulbs, they stand on top of each other. All right, so they have one kid standing on top of another kid's shoulders. Now, I can't legally do that in the classroom, so we just have the kids pretend that that's what's going on. All right, so initially, yeah, the electrons are very high up there because they contain a lot of energy. So I'll just draw the arrow pointing upwards really high, just to say that they have lots and lots of energy. By the time it reaches the first load, the load uses a big portion of it, so then there's only a small amount of energy left for the electron to travel through. And then by the time the second one uses up the rest, now they've all run out of energy, so we just put them down low, and the kids just carry them down low until we bring it back to the source again. So I don't know. I hope that with my drawing over here, it gets the idea across of what's happening here, right? That the two loads, they're sharing the energy. So one of them consumes some of the potential difference, and the second one consumes the rest of the potential difference till it drops down to 0, and then the process gets repeated by the EMF again. And then I just do one more demonstration just for kicks, where I just take case 1, and all I do is I just add another cell to it. All right, so this time around, I have two sets of students virtually on top of each other. Okay, so then if the electron is low over here, through the first cell, it's brought up somewhat high, and then at this point over here, it's brought up to the kid's tippy toes, really high. So it's an electron with a lot of potential difference. So with that great potential difference, that load will have to sink all of that to the bottom, and that's why when your voltages are too high, you may end up damaging your electronics prematurely because the voltage is too high for it to handle. All right. Some people got to do this back in grade 9. That's awesome. So you know what I'm talking about. Others, if you missed out on it, well, I hope you can imagine how fun it was. Yes, one student has a question.
Just going back to case 3.
Yep.
So would the first light bulb that gets the initial electrons when they're like still have a lot of when they're still very high voltage,
Yep.
would that shine brighter or lighter than the second one?
No, not necessarily. All right. The definition of how they'll shine more or less really depends upon their internal resistance. So in other words, if R1 is equal to R2, they will share things equally. All right. Meanwhile, if the resistance of this resistor over here, let's say that's 1,000, ohms versus 100 ohms. This is the counterintuitive part. All right. Again, the 1,000 ohm resistor, yes, it has a higher resistance, but also because it has a higher resistance, it will have a higher potential drop. All right. So if these were physical light bulbs, there's a good chance that the first light bulb will light up far brighter than the second light bulb, and you'll know that only through experience. All right. Other than building up a circuit like that, I don't expect any high school student to know that answer. Okay, so there's your answer to your question, right? How will one light up more than the other? It all has to do with regards to the internal resistances of the loads. Okay, that will dictate which one will consume more power and which one will consume less.
Okay, thank you.
This way, then yes, by definition, the second light bulb will consume less power and it won't glow as brightly. That is true. All right. Again, I don't want to go into those aspects of it. I think those of you that are asking those questions, you might have taken electronics class. And that is something I do encourage for you guys to do, whether if you take electronics class physically or you guys go and buy those kits that are online or go to, not Radio Shack, the Source, Circuit City, or there's a hobby shop. You guys are in Canada. I may as well promote this place because I don't want them to go down under. Oh, what's it called? I'll tell you guys afterwards. There's one of those stores, and it's at Warden. No, not Warden. Man, Victoria. Okay, Victoria Park in Shepherd has one of the stores. Sayal, that's what's called. Sayal. All right, sure. I'll do some free advertisement for them because I know that they're probably suffering big time through COVID. All right, Sayal Electronics and Hobbies. If you go there, they'll always have these kits for electronics. I do encourage that if you love electronics, get a kit, play with it. Damage it by accident. You learn stuff from breaking things. I kid you not. Your parents will be angry, but once you break it, you learn your lesson and you know better not to do it next time. So, you're asking me all these random questions here. I know the answer to it because I used to play with Christmas lights as a kid, so I know that that's the outcome. All right. But again, in a grade 11 student, I don't expect them to know, so I'm not going to share that level of detail. Okay. All right. So just know that this is the regular characteristic behavior of how things flow. Okay, since there's so many units and variables that are all thrown around so far already, let's clean it all up together. All right. As I mentioned to you guys, at some point in your course pack, there's going to be a place where you can just keep everything all organized, and here it is. All right. So this can be found on course pack page 51. A lot of it has already been filled in for you. Okay. So I'm going to go rather quickly through this. All right. So if you have it printed out, fill it in, and if you don't have it printed out and you're trying to quickly jot it down, I'd say just leave space for it, and then you know where to find my PowerPoint afterwards to fill in the blanks. And again, this is being recorded, so you can pause the video and watch it then. All right, because I'd rather have this thing flow more naturally, and many of us already know what these are going to be anyways. Okay, for example, work and energy. Depending on what you're trying to describe, you'll either describe it as W or E subscript something. Okay, that's the variable that you use. Energy or work is always measured in joules. I may as well let the animation run through. And the symbol for joules is capital J. As I mentioned, with regards to unit names, I know that the joule came from James Prescott Joule. all right, and his last name was capital J. But whenever you describe it as a unit, you leave it as lowercase. I know it's strange, but as a unit name, it's not a proper noun. Okay, now a joule is not a fundamental unit. We know that work is equal to force times distance, or a joule is equal to a Newton times a meter. And a Newton also is not a fundamental unit, right? A Newton is equal to a kilogram times a meter per second squared. So if we replace that letter N with kg times meters per second squared, you end up with this mess over here. 1 joule is equal to a kilogram times meter squared over second squared. Some of you guys already have this written down in your notes somewhere else earlier, all right? It's a difference between a derived unit and a fundamental unit. Next topic, the world of time, all right? Time is a measurement of the continuum measured in seconds. For delta T, it's for a one-shot activity, and for capital T, it's something that you expect to repeat itself over and over again, so therefore it's periodic. All right, we like to stick with time in seconds as our SI notation, and seconds cannot be broken down any further. Fundamental units are units that cannot be represented by anything else. It is the fundamental unit, or it's the most basic of units. Right, so seconds is already a fundamental unit. It can't be described with any smaller value. Some students will say, well, can't you describe seconds as milliseconds or microseconds? Well, you're still talking about seconds. I'm saying to break down seconds and represent it by something else. Okay, a millisecond just simply means less than 1 second, right? By a million times, a millionth of a second. Sorry, a milli is a thousandth. So a millisecond is a thousandth of a second. A microsecond is a millionth of a second, but it's still seconds at the end. Okay, just to focus more on this topic over here, I think in your course pack I already wrote down force. Yeah, force is a push or pull. That's already on course pack page 51. Okay, so the stuff I'm adding in here is the stuff that's directly related to this unit. Potential difference is the fancy word for voltage. Okay, so you can either write down the variable capital V for voltage, or you could also write it down as EMF, but we won't be using that here, right? It's just that in some classes of grade 11, like the grade 11 AP, they use EMF instead of V. It would have been nice if all of them shared the same variable and unit symbol. This is the only one I can think of that shares the same one. It would have been nice if the rest of them did that as well. Now, here's the thing. With regards to fundamental units, as I mentioned before, in high school, we only have 5 of them. M, K, G, S, A, and capital K. That's it. So a volt, you can clearly see, doesn't exist here. So how do you exactly describe a volt? All right. A volt, by definition, is how much energy there is per a bajillion electrons. C is a constant. C is for 6.28 times 10 to the 24 electrons. All right, so it's a whole bucket load of electrons. So voltage, by definition, is how much energy there is in that bucket load of electrons. And as you know, a joule is not a fundamental unit. Same as a coulomb. A coulomb is not a fundamental unit either. All right, but I do want to show you this breakdown here because tomorrow, or no, later on today, we'll have to solve homework knowing this fact, that a volt by definition is how much energy there is per a lot of electrons. Okay, so what are the fundamental units of voltage? If you're really curious, here it is. Will I ever test you on it? No, I won't. But for those that are curious, as you can see, a voltage can be described using these 5 fundamental units. All right, it doesn't have to use all 5 of them, but it is based upon them. Current is denoted with the variable I. Current is measured in amperes. And why is current measured with the letter I? It's kind of weird, isn't it? Why not just use the letter C? It was briefly mentioned in the grade 9 textbook. So when I taught the grade 9 textbook, I actually read the little margins. And if you look at the little margin over here in the grade 9 textbook, it tells you right there. The symbol I is used to, the symbol I is used for current because it stands for intensity. Nice to know. I did not know that myself. Good job, grade 9. All right, current is measured in amperes, denoted with a capital A. I know I erased it down below, but the 5 fundamental units are M, kg, S, lowercase s, capital A, and capital K. So current is a fundamental unit. All right. And I know it sounds weird, but that fundamental unit can technically be broken down. All right. So an ampere is also equal to a coulomb per second, even though an ampere is a fundamental unit. Some people might be confused with this. All right. How can you say that an ampere is a fundamental unit, yet it can be broken down? It has to do with the definition of what a fundamental unit is. And we'll talk about that towards the end of this unit. Okay, so I'm not going to go into those dirty details yet. And the reason why I'm showing you this formula here is because we got to understand this concept as well. And current, by definition, is how many electrons are flowing in a circuit per second. So when you have low current, few electrons are flowing. When you have high current, tons of electrons are flowing. Okay, that's what an ampere is by definition, or current is by definition. Resistance is the opposition to current flow. The variable for it is R. Resistance was first observed by George Ohm, and that's why it's named in honor of him. However, we do not like using the letter O for unit symbol, because the letter O, what is it? Is it a 0, or is it an O, or is it a naught? And that's the problem about drawing a circle. All right, so they couldn't use that. But if you look at the Greek letters, if alpha is for the beginning and omega is for the end, then hey, why not? So even though it has absolutely no relation to George Ohm, we decided to use the omega symbol for resistance. And yeah, we'll use the Americanized written version of it, which looks like that. I know that some of you who've gone to Greek school, omega does not look like that. I get it. It's the Americanized one. Okay, and yes, by definition, to find out resistance, what you do is you divide the voltage by current. That's how you'd figure it out. But an ohm is not a fundamental unit. An ohm can be described using a bunch of letters. Now I'm going to cross this out just to tell you that no, you don't need to memorize it. And no, you don't have to copy it down either. It's not important. Okay, I'll leave it just so it looks clean, but I'm not going to test you on that. Power. We just learned about power. Power is measured in watts. Power is not a fundamental unit. All right, power is the rate at which work is being accomplished. So power can be measured in work, measured in joules, over time, in seconds. And as you know, a joule is equal to a newton times a meter. A newton is equal to a kilogram times a meter per second squared. So if you keep on subbing, you end up having this. Okay, and the last measurement, all right, the coulomb. Charge is measured either using little q or capital Q. You use little q when you're talking about, a small handful of charges, like 1, 2, or 3 million electrons. Okay, just a handful of electrons. All right. Meanwhile, if you're talking about a large quantity of charges, then you'll use a big Q. That's all. All right. It's rather arbitrary because textbooks, they'll just switch between little q and capital Q. I'm not going to be very fussy about it, but I'm just letting you know that that's the reason why the two exist. All right. Because some textbooks want to be very specific, talking about the little charge and the big master charge. All right. Charge is measured in coulombs, and that's probably the reason why they couldn't use the letter C for current. Because charge in coulombs was first discovered before current was discovered. All right. In the hierarchy of things, this was understood first. I don't know if I said the right number earlier. It's 6.24 times 10 to the 18. I guess if you go back in the recording and I said a different number, I apologize. That should be the right number. Okay, so there are 6.24 times 10 to the 18 electrons in 1 coulomb of charge. It's like saying there are 12 eggs in a dozen, except this is a big version of dozen. Okay. In fact, this number over here isn't that new of a number. All right. You might have learned in a previous unit that 1 electron volt, one electron has a charge of 1.602 times 10 to the negative 19 coulombs. All right. You might have learned that. So what if you end up doing the reciprocal of this value over here? You can try it on your calculator. Okay. Because if 1 electron is equal to that number, then 1 over electron means per electron, right? So yeah, when you do the reciprocal of this, you'll find out that you'll need to have 6.24 times 10 to the 18 electrons to equal the number 1. In other words, these two numbers over here, they're reciprocal numbers of each other. So you don't really need to have both of them in your notes, really. You just need to have one of the two, and then you just do the inverse to find the other one. All right, so for more adventures in the world of fundamental units, I do have a lot of videos on it. It's not made by me, but if you go onto my channel and you scroll all the way to the bottom, it says, you know, what are fundamental units? And I think on those videos, I'll get through all 7 of them. All right, so for those that really want to know the background story, you can take a look at it over there. That's about an hour and a half of video fun made by a bunch of universities, as well as one episode by Tom Scott. Okay, so if you got the time, I encourage you to watch it. No, you're not going to be tested on any of that stuff. All right. Any other questions on this slide here before I move on? If you need to take a snapshot of it right now, by all means. All right. And again, this is just on the bottom of page 51. You're just filling in the blanks afterwards. And really, this is just a guide or a memory aid for you. That's it. Any questions or anyone still need this up before I move on? Okay, I'll wait for you to be down, and then I'll move on. And while you're jotting it down, is this the only chart that exists? Oh, it can grow. It can grow quite a bit. In fact, in grade 12, we start from here and we add another, I think, 2 more pages of these on top. All right, so there are new units to come. New units to come. And no, this was not all discovered in a day. Most of the stuff, it took about a century to cover, at least this material here, that's 2 centuries worth of information. Okay. So yeah, that's why it seems like it's a lot of new information all at once, and it's because we're summarizing what has been discovered for the past 300-400 years. Okay, I can advance on now. All right, so there are 2 standards that we go by with regards to how electricity flows, and it has everything to do with history. All right, once upon a time, a young gentleman named Benjamin Franklin, you may have heard him before. He was an active politician. He was also a super nerd, so he did a lot of experiments. He invented the bifocals, and I think the most memorable of his experiments that most of us know is that one day during a rainy day, he decided to fly a kite. And to make matters worse, he flew a kite where the kite string was not just a regular string, it was a piece of wire. All right. He wanted to prove that lightning was electricity. So yeah, he was a dude with the kite, letting lightning strike against it so that the current can flow through the wire into a little clear jar. And in the jar, there apparently was a little key. And the key the jar was filled up with some form of inert gas, because anytime they excite an inert gas, it begins to glow. So anytime the lightning was about to strike, or it did strike the kite, you'd see some light being emitted by the gas that's inside. And that was his wacky experiment. All right. And what did this experiment prove? It just proved that electricity can flow. That's what it proved. The problem is that he didn't have the technology back then to figure out which way did the current really flow. Did it flow from the sky to the ground, or did it really flow from the ground to the sky? He had no idea. So he said, yeah, you know what, let's just call this side positive and this side negative if it's going this way. And if it's going the other way, we'll call this side positive and that side negative. All right. So he realized, you know, like in a number line, there's a positive number line, there's a negative number line. They're at both extremes. That's all he knew about electricity. There are 2 extremes. So he just decided to call one end positive, the other end negative, and just said that current flowed from positive to negative. Just did a coin toss. Unfortunately, today we know that coin toss is incorrect, right? That current doesn't flow from positive to negative. Current actually flows from negative to positive. And that's what's known as electron flow. I'll give you guys a moment to jot all this stuff down. Some of you might be wondering the whole LHR and the RHR thing. Just copy it in your notes for now. I know it makes absolutely no sense. That's for next week, actually. So we're just taking notes right now to get ourselves ready for next week.
Call from mommy.
We're in the middle of class.
Mommy.
Those are good phones. When they're on sale at Costco, get them. The cool thing about them, you gotta make sure that they have Bluetooth. Okay, you gotta get linked to cell, because if it has Bluetooth and linked to cell, that means you can hook up your cell phone to it. And if you can leave your cell phone anywhere in the house. That way, you know, when your cell phone rings, you don't have to chase after it. You just have to find one of the cordless phones in the house. So it's a pretty neat technology. It's good stuff. Okay, so just to summarize the pictures on the right, again, once upon a time, back 300 years ago or so, we once thought that current left from the positive and traveled all the way to the negative. All right, that's what we once thought. Just to let you guys know, I didn't mention it before, but anytime that you draw a cell or a battery, the longer lead is always the positive end and the shorter lead is the negative end. All right. So unfortunately, when it comes to test time, I won't tell you that. You just need to be able to read it that way. All right. So the longer side is always interpreted as the positive side. So yeah, 300 years ago, Benjamin said, you know what, let's just go from positive all the way to negative and call it a day. And it wasn't until about 150 years later that good old J.J. Thomson comes by with his crazy experiment to prove that atoms, well, they're not a plum pudding. Instead, there's a dense little nucleus in the middle, big void in space, and a tiny little dot on the outside called the electron. All right. And if you think about it this way, you can't have the protons move in a circuit. It's stuck in the middle. Here's the other problem. If you have the protons move in a circuit, now you're losing or gaining protons. Now you're changing the element. Remember, elements are defined by the number of protons. So if you end up subtracting or adding protons, you're making a brand new element. If you ever passed electricity through a wire before and you stare at the wire, does the wire really change color? I'm not talking about you short-circuiting or anything. Just in general, when you pass current through a wire, does it change color? Right? If you have a steel wire, it remains steel. If it's a copper wire, it still remains copper. So as electricity flows through a circuit, protons cannot move. All right? Then alchemy will exist. So instead, the only person that can move is whoever's out there in the cloud, which are the electrons. So that was discovered 150 years way too late. Okay, so 150 years in the future, J.J. Thomson says, nope, we got it all wrong, guys. Let's reverse engineer everything and have everything flip all the way around backwards. Let's just say that current flows from negative to positive because it's the only way that's logically possible without violating chemistry. Okay, and in doing so, yeah, there are these rules called left-hand rule and right-hand rule, and they had to go and swap them. Okay, so you know, from 1750 until 1897, they used the right-hand rule to predict things, and then 1897 and beyond, they said, nope, got it all wrong. Put the right hand down. Now start using the left hand. And when I was your age, that's what I learned. Okay, so when I was in high school, I had to use everything using the left-hand rule. And then when the curriculum changed, they said, just put that hand down and go back to what was wrong back 300 years ago. All right, so for our purposes, we're going to solve everything using conventional currents. Okay, as weird as it is, that's what we're going to go by. Okay. Of course, that created, you know, a whole fight online and in the nerd community. So here's the explanation to say how both of them are correct. Watch this animation here. Let's say I take that little snippet from the piece of wire from that lower diagram. Again, as we said, in real life, it's the electrons that are able to move. And normally you have electrons flowing through metal. And if you, as you know, metals, they have a valence shell that's not full. In other words, they have little gaps in them. Okay, so this will represent that tiny little gap. So take a look at the electrons as they're flowing through the circuit. Okay, so according to the diagram we have up above, the electrons will be flowing to the left. That is completely true. But you're also seeing an optical illusion. What do you notice? I'll repeat it again. Okay, the electrons are flowing to the left. And as the electrons are flowing to the left, you start seeing this thing, this little bubble moving to the right. That's the excuse for current flow from now on. All right. So to make sure that both of these sets of nerds are correct, electron flow is when electrons are flowing. And to take a look at that gap, when the gap flows, that's the definition of what charge is. And that's our definition to this day. Another way of seeing this and better appreciating it is if you ever owned an aquarium before and you had a little bubble maker thing, right? and you see the bubbles going up. Truth is, it's not that the bubbles are going up because they want to go up. They're going up because they're getting squished to go up. It's really the water that wants to go down, and as the water goes down, it just moves the bubble, kind of like you put squishing on toothpaste, squishing it upwards. That's what's really happening. Okay, so nothing is forcing the bubbles up. It's because gravity loves the water more. For this course, we're going to focus strictly on direct current for our calculations, but at some point we will need to talk about alternating current because it's the only reason why some technology works. All right, so direct current is when current flows in one direction. Pretty much any portable electronic device you have operate under DC. There are a few exceptions here and there, but for the most part, they operate under direct currents. However, the way how electricity is delivered to our house, Nikola Tesla won. Okay, there was a big fight between Nikola Tesla and Benjamin Franklin about how electricity should be delivered to the house. And through the two, one of the two won in their technology. Okay, Thomas Edison, he wanted to have all houses have DC current, so high voltages DC current to reach the houses. That's what he wanted. Nikola says, no, that's not efficient. That's silly. That's nonsense. Let's use AC instead. It's more efficient. And as you know today, we can see who won. Anyone else still need the slide before I advance on? Okay, sure. Go ahead and jot this down.
You explain why both methods are technically right?
Again, it depends on how your perspective, right? Like for example, in an aquarium, is the bubble really going up or is it just the water that's going down? This is the same thing, right? Is it the electron that's moving to the left, or is it the bubble that's moving to the right? Which one are you trying to observe? Because they're both going in opposite directions. Of course, you know, I guess that's the reason why the curriculum has changed to what it is today. And it's that if enough people are wrong, eventually wrong becomes right. All right. Because again, for the first 150 years or so, we were doing it that way. Or 100 years, 150 years, we're doing it that way. And then after that, somebody back, only about 100 years ago, all right, it's not that long ago that J.J. Thomson discovered that we had it all wrong. All right. But then by then, so many scientists have already contributed in their discovery of how electricity behaves that I guess today we're going with, you know what, if enough people are saying use the right-hand rule, let's just stick with the right-hand rule. Okay, so we're going to use the right-hand rule for our class. We're going to assume conversion current. Yeah, there's a lot of cool videos. As there's even videos about the fight between those two scientists, right? Is that enough time for everyone? So I'm just trying to look for an image. Did I accidentally delete the image? Maybe it's in another PowerPoint slide. It's about the timeline, that's all. You know what, this should have been right here, so why isn't it here? I delete this and insert it right now. Sorry that I'm interrupting our learning flow, but it's like, man, that's an important picture. What happened to it? Here it is. Why not? I'll just copy that again over here. Dump it right there. There you go. All right. Here's the timeline. Come on up. There you go. There's the timeline. Do you need to copy it down? No, you don't need to. In my classroom, some biology teachers, they like to have, the time how the Earth evolved up there on their wall. I just have the physics version of it. All the nerds that have contributed towards physics, here are their names. And again, if you take a look at the timeline over here, Benjamin Franklin's kite experiment was 1752. And the electron wasn't really formally paid attention to until about 150 years afterwards. Okay. And then beyond that, hey, that's when we started discovering all these other things. If you remember me talking about the gold foil experiment, that's when it was discovered. And these two concepts were covered in grade 9, right? James Chadwick says, hey, the nucleus is pretty heavy. There's some dead mass in there. All right, so the neutron was discovered quite recently, less than 100 years ago. And that's how new chemistry is as a science. Okay, so now let's summarize all the formulae. And I think we're going to go through 2 math examples, and that's it for this lesson here. All right, so we've already covered V equals IR. All That's fine. Other things I want to point out is the definition of what a volt is and what a definition of what a current is. So that will be a new formula, all right? Because the definition of what a volt is how much energy there is per bajillion electrons. In other words, the voltage is equal to the amount of energy per packet of coulombs. So delta V is equal to E over Q. Some textbooks show delta V, other textbooks delete delta V. But in the name, if you listen to it, it's called potential difference. So that's why some textbooks are sticklers about it and put delta in there. I think your textbook threw it in there for that very reason. All right, so a volt, by definition, is how much energy there is per bajillion electrons, or per coulomb of electrons. And as you may recall, current, by definition, is how many electrons flow as time goes by. Okay, keep that in the back of your head, because also in grade 9, we learned this formula here, P equals IV. Here comes the fun, nerdy part. Okay, so you would have learned back in grade 9 that, yeah, power is measured in watts, so you just nodded your head and smiled. Current is measured in amperes, you nodded your head and smiled. And voltage is measured in volts. So somehow the letter A times the letter V became the letter W, and you probably just nodded your head and smiled and wrote down the answer because that was the only way to get an A, and you moved on, right? But you didn't really talk about the backstory of it. Well, right now, let me tell you about the backstory and why this is true. And I'll answer your question as well, okay? Remember that A is not just A. A is a measurement of current per second, okay? So current, I, a measure of the variable I, or an ampere, is how many electrons are flowing in a given second, or how many coulombs, which is a whole package of electrons, are flowing per second, okay? And a volt, by definition, as you can see up there, it's how much energy there is, measured in joules, per packet of electrons. Now, if you recall from our previous unit, what is power? Power, by definition, is how many joules there are delivered per second, right? The rate that energy is being used. We'll take a look on the right-hand side. Coulombs, divide out with coulombs, and holy cow, what do you get? Isn't that amazing? As I said, units work out 100% of the time. Okay, so I know that back in grade 9, you just knew that P equals IV, and you just nodded your head and accepted it. But now that you understand, what an ampere really is, where an ampere is how many coulombs of electrons are flowing per second, and what a voltage really is, which is how much energy there is per coulomb, then you're still with the same definition. Okay, and that was the one thing that scientists wanted to accomplish. They wanted to create a universal standard. They didn't want power for this universe to be different than power of another universe. They wanted power for electricity to be the same power as you running up the stairs, which is the same amount of power that is used to heat up water, for example. Okay, they wanted the same value. That way we have a universal convention to go by. So yeah, a watt is equal to a coulomb per second times a joule per coulomb, which is also equal to a joule per second. So the units do work out. And the last formula, we kind of covered this as well. Power is equal to work over time, or work is equal to power times time. Or in this case for electricity, the energy used. So E is really for the energy used as opposed to an energy state. So it's really technically E total. Okay, but we'll just call it E because your textbook calls it E. All right, so energy used is equal to power times time. And here's the last one, okay, Q equals NE. As I mentioned, with regards to Robert Millikan's experiment, he was a scientist to prove that there is the smallest quantity of charge called the electron, all right? So if you have one electron, you have this number here. If you have two electrons, well, then you have double that number. If you have three electrons, then you have 3 times that amount. And I hope you get the idea here. If you have 4 electrons, you'll have 6.4 times 10 to the negative 19 coulombs, etc. What is this trying to get at? There is no such thing as a number in between here. In other words, you can never get 3 times 10 to the 19 coulombs because you can't get fractions of electrons. Okay, electrons are either there or they're not there. This is the whole idea about quantization. You might have heard me throw that word here and there. If you're into music, there is this thing that you have to do with music so it sounds right. which is to quantize the music. What does quantize mean in the world, in the music world? It means that, you know, when you're playing, you're so nervous and sweating that you're playing all your songs or your notes out of beat, right? And everyone's just used to a song being played to a certain time in a certain measure. So when you quantize your music, you're locking down your notes to the nearest something. So for example, you're locking down to the nearest quarter, or you're locking down to the nearest eighth. So if you ever end up using any of those audio recording software, not like Pro Tools may have it, as well as those MIDI editing programs, I forgot what they're called. There's a feature in there called quantize. All right, and quantize just simply means lock it down into these numbers here, because we want the measures to be uniform and even. All right, and the same thing happens in the world of physics as well. The strange thing about electrons is that electrons, they are not a continuous measurement of values. Instead, they are also quantized as well. All right, so have you ever heard of quantum physics before? That's what they're alluding to. You're either this, or you're this, or you're this. You're never in between. So this kind of introduces that idea. As such, this letter for n, this n over here, has to be a whole number. Okay, so n has to be a whole number. Again, Q is a quantity of charge measured in coulombs. All right, measured in coulombs, or C. So if you have one electron, you have 1 times 10 to the negative 19 coulombs of charge, right? Q is equal to 1 times E, which is equal to 1.602 times 10 to the negative 19 coulombs. If n is equal to 2, if you have 2 electrons, then the charge is equal to 2 times E, which is equal to 3.204 times 10 to the negative 19 coulombs. So I hope that that answers your question. Okay, Q is the quantity of charge, but that quantity of charge are all fixed quantized values. Do we really need to know that for this course? No, not really, but I'm kind of preparing you guys for the world of chemistry, because you will see that formula again in chemistry class. All right, so there are certain things where physics and chemistry overlap, so I'm just preparing you for that aspect of it. Okay, so just know that n has to be a whole number. Integer, sure, you could call it integer as well, but it has to be a whole number. Okay, so let's go through 2 math problems. Okay, and yeah, these math problems, they're going to be weird. Will they be applicable to life? Probably not, but I just want you to be able to see how these formulas link together, all right, and how these ideas and concepts all jive. Okay, so this question is asking for, what's the potential difference of a cell if it's able to deliver 1 joule of energy for every this many electrons? Okay, so you know that voltage by definition is equal to E over Q. That's true. But Q is not for a number of electrons. Q is for a charge measured in coulombs, right? So 1 electron has this charge. 2 electrons has this number times 2. 3 electrons has that number times 3. So that's what we got to do first before we even use that formula there. Okay, we have to use our Q equals NE formula first. So that's step 1, and this is step number 2. I'll erase everything, because let's do everything properly. Starting off with our givens. What do we know? We know our E is equal to 1 joule, and we know that our number of electrons is a lot. 4.16 times 10 to the 18 electrons. Okay. First step is to find out the equivalent charge measured in coulombs, which is equal to N times E. So 4.16 times 10 to the 18 electrons zipping by in a circuit, multiplied by 1.602 times 10 to the negative 19 coulombs. What is that equal to? And we have a charge of 0.6664 coulombs. Now we can move on to the next formula, which is V is equal to E over Q. We know that these electrons, they contain 1.00 joules of energy for every 0.664 coulombs of charge. So the voltage is equal to roughly 1.5 volts, or 1.5 joules per coulomb, and a joule per coulomb has the same exact meaning as 1.50 volts. Okay, if you recall, I already told you that 1 volt has the same meaning as 1 joule per coulomb. They're equivalent units. Anyone else still need this slide or have any questions before I move on to our last question? Yes, please ask away. Or you just need more time. I think you need more time.
I just need to write down the last
Yep.
things.
No worries. Okay, ready to move on. Yeah, this has already been pointed out. In fact, this is just a different version of it. What I did was I just equated the equations together. In other words, if I knew that Q is already equal to NE, I could just sub it in right over there and more directly get to the answer. And if you do it this way, it's perfectly fine. Just tell me that Q is equal to NE. That's all. So V equals EQ, Q equals NE, then that's equal to that, and that's fine. Okay, so you could combine them together. You don't have to calculate them out separately one at a time. All right, and our second question and our last question of the day, or of this time block. Hope that buys enough time. Don't worry, this is the last slide. So if you need to leave some space to fill in the question, then you're more than welcome to do so. Again, this is another rather ridiculous question, all right? But it's just to show the units as they blend together, right, to get to our conclusion. Starting off with these questions, we start off with our givens. Okay, we know that energy is equal to 912 joules. Current is equal to 1.25 amperes. And we don't want to deal with measurements in minutes. Instead, we want to deal with measurements in seconds. Now, you'll notice that I ended up graying off the 12 value because this question is asking, can we get the value of 12 based upon these values over here? That's all the question's asking for, all right? Can we get 12 volts out of all this stuff here? Now, everyone's going to solve this their own unique way, all right? And since I'm doing this all real time, it's probably going to be different than how I decided to solve it according to my pre-recordings on PowerPoint, okay? Because I'm just looking ahead right now, I know that by definition, potential difference is equal to energy over charge. So I kind of need the charge value before I can get to answering yes or no, if it's 12 volts or not, okay? So I know that, yes, Q is equal to NE, but we don't have number of electrons here, okay? But there is another definition of Q, if you recall writing it down, where Q is equal to I times delta T. All right, because by definition, current is equal to charge over time. Okay, so it's just simply rearranged. Okay, so if, sure, I'll just write it like this. I is equal to Q over delta T. So these are just our reference equations there. Okay, so I'll start off by solving for our Q. So 1.25 amperes times 60 seconds. Half of 60 is 30, half of 30 is 15. So 15 plus 60 is 75. 75 coulombs. Okay, now we have our value of Q. So our voltage, which again, if you want to write down the delta, it's up to you. I think your textbook is just that extra. All right, so their potential difference is equal to 912 joules. Oh, I better write the formula first. E over Q, which is 912 joules over 75 coulombs. So 912 divided by 75 will give us 12.16 joules per coulomb. And a joule per coulomb is also equal to a volt. In other words, given these conditions of a solar cell, it will produce just enough voltage to use your cell phone charger. Okay, most solar cells, they measure their ability to produce electricity in watts. In other words, it could produce either high voltage and low current or high current and low voltage. It's just up to the manufacturer on how they design it. That's all. Okay. But we want to figure out voltage from here, and there are two ways of solving it. Okay. There's plan A, which is okay, just knowing that power is equal to current times voltage. Okay, so power is equal to 1.25 amperes, and we'll just recycle our 12.16 volts. All right, 1216 times 1.25, 15-ish, yeah, 15.2 watts. That's one way of solving it. Of course, we're reusing a number, and if we made a mistake along the way, then we'll be in trouble. All I'm saying is that there are other ways of solving the same exact problem. If you recall, power by definition is the work that you do over time goes by, or the energy that's used over time. So you could also do 912 joules divided by the 60 seconds in your givens. And 912 over 60, I won't be surprised if it's the same exact number. 912 divided by 60 equals, hey, look at that, the same exact number. All right, so preference in solving this is completely up to you. For tonight's homework, work on course pack page 52, questions 1 through 5. If you're wondering about question number 5, do you need to do the research? I'd say just read that passage in your textbook, and that will be sufficient. All right, so just read the passage, and that is it. Any other questions before we end off the recording? If that's all there is, then thank you for joining me in this episode. Catch you next time.